Page 10 of Math Induction, 1C. If endpoints are placed inside a triangle and non-intersecting lines are drawn connecting the three vertices of the triangle and the points within it to partition the triangle into smaller triangles, then the maximum number of triangles resulting is 2n plus 1. So if you remember on the first page of this, no, it's not the first, page 2 of the packet, we did the first few cases of this in order to create this proposition. So if you have one point in the triangle and you connected that point to the vertices, you create three triangles, right? So when you have n equals 1, you create three triangles. Okay. If you have 2 points within the triangle, then you create more triangles. How many triangles? It would be 1, 2, 3, 4, 5 triangles. So T2 is equal to 5 triangles. And if you have 3 points within the triangle, then you create even more triangles. Let's see, 1, 2, 3, 4, 5, 6, 7. T3 equals 7. So then we have our proposition here, right? So first of all, we're going to do the base case, and if n equals 1, then we're looking at this case here. So indeed, we're going to use the formula, and T1 tells us that it's T1 plus 2 times 1 plus 1, which is equal to 3, and that's exactly what we get by counting out the triangles. So it's proven. So we do know that P subscript 1 is true. Now we're going to assume that the kth case is true, which means that if we have n equals k, then we know that, so if n equals k, then we know that tk is equal to 2k plus 1. So we're going to use this in our k plus 1th case. In the k plus 1th case, let's draw a sketch of what one of these triangles might look like in the kth case. Okay, so basically let's have this case here. Okay, so there's a bunch of triangles over here, but there's a point here, and there's the case where we might make the k plus 1th point. We put it in the middle of this triangle, and if we did put it in the middle of the triangle, then that would create 3 triangles where there used to be 1. Okay, so this 1 triangle became 3 triangles, which means that we added 2 triangles. So if we add 1 blue point, we're going to create 2 additional triangles. So if n equals k plus 1, then we're going to add 2 triangles to the original number of triangles. And there's one other possible case, which is, got a bunch of triangles in there, and then we have one of the last points here. We could also add the point right here on the line, and in this case, we create 1, 2, 3, 4 triangles where there were 2. So from 2 triangles to 4 triangles. So we're also adding 2. So again, the original relationship is maintained. So let's take our little drawing and we'll put it aside. Okay, so now what we're going to do is we're going to take this equation here, and we are going to substitute in t of k, which we assume to be true. We get 2k plus 1. Now, if we rearrange this, we could separate it into 2k plus 2 plus 1, and we could factor out the 2. Now, if you look at this, and you look at this, you can see that the only difference is, instead of k, we got k plus 1. So that is the definition of proving that this works for the k plus 1 case, is we take this expression and we find out through algebraic manipulation that this is also true. Okay, so it's proven. So thus, t k plus 1 equals 2 times k plus 1 plus 1 if t of k is equal to 2k plus 1. Since p1 is true and pk plus 1 is true whenever pk is true, then pn is true for n is greater than or equal to 1. N is a integer. Okay, let's go to number 3. Use the principle of math induction to prove the following proposition. You may use the results from chapter 6 that for all complex numbers z1 and z2, z1 plus z2 conjugate equals z1 conjugate plus z2 conjugate, and z1 z2 conjugate equals z1 conjugate z2 conjugate. So in number 3 here, we're going to start by defining the p subscript n. Basically, p subscript n is, this here. Okay, that's p subscript n. So if n equals, the base case would be n is 1. If n equals 1, then we basically have this statement, z1, but we only have the first term, z1 conjugate equals, and then we just have the first term of this one, z1 conjugate. That's pretty trivial. z1 conjugate is equal to z1 conjugate, and that is true. Therefore, p subscript 1 is true. If pk is true, then, and so now we're going to write this statement here, except instead of z subscript n, we're going to put p subscript, or z subscript k. So we're going to have z1 plus z2 plus ... plus zk conjugate is equal to z1 conjugate plus z2 conjugate plus ... zn conjugate. Zk conjugate, sorry. Okay, so we're going to assume that's true. Now we're going to write the left side here in terms of k plus 1. So we're going to have z1 plus z2 plus ... all the way to zk plus zk plus 1, because we're doing the k plus 1th case. And then we take conjugate. And now we're going to see, is there a way to use this assumed truth here and maybe substitute in something? So what we're going to do is we're going to take the part of this that looks like this, which is up to here, and we're going to separate it out with parentheses. So we're going to put z1 plus z2 plus ... plus zk parentheses, and then we'll leave zk plus 1 separate. And then we're going to use this. Remember they gave us this hint here? We're going to use that, and we're going to say, okay, this is the first complex number, and this is the second complex number. So I have two complex numbers added together, although one of them looks like a bunch of complex numbers already added together. And we're going to use this rule and separate them out and make each one a conjugate. So what we're going to do is we're going to say z1 plus z2 plus ... zk conjugate plus, this is equal to, zk plus 1 conjugate. Okay, so we use this rule to break this up, right? All right. Now that we have this left side looking exactly like this left side, now we can do the substitution. So now we could say, actually, the parentheses expression there is z1 star plus z2 star plus ... plus zk star, and then we have plus zk plus 1 star. Okay? And basically, we have proven it because do you see how the k plus 1 version of this would be this left side and this right side? Because this one goes up to k plus 1, and this one also goes up to k plus 1. So we can come down here and we could say, thus, z1 plus z2 plus blah, 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 plus zk plus 1 conjugate is equal to z1 plus z2, z1 conjugate, z2 conjugate plus dot, 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 plus zk plus 1 conjugate. If, and then we're going to put the exact same thing, except now we're going to put z1 plus z2 plus dot, 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 all the way to zk only conjugate is equal to z1 conjugate plus z2 conjugate plus dot, 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 plus zk conjugate. Okay? So since p1 is true, and pk plus 1 is true whenever pk is true, then p of n is true for n is all positive integers. Oops. I was so used to drawing conjugates, I made that into a star. Okay, and that is it for page, is that page 10?